Now that you got a chance to make your own ellipse, let's take a look at defining these a little bit further. So A, again, defines half the major axis length. B defines half the minor axis length. And we have them drawn on here. This is another image that you probably are going to want to record down or just at least add some of these details to your ellipse. And then C is the distance from the center of the ellipse to either focal point. So we have this as center to the focal point. So 2C is focal to focal. For a circle, A and B are equal to the radius. This value and this value are equal. A would be just half of it, right? So A and B are equal to the radius. They are the radius. And both focal points are co-located at the center of the ellipse. So this image here is showing you the different diverse orbit options that we have. And we're going to get into all of these a little bit later. So you can just kind of have fun watching these go around. It's pretty neat. Here's some of them labeled. So as you notice, there's a LEO, there's a MEO, there's a HEO, and there's a GEO. And all of those are different ones that we're going to examine. So orbits are described by a set of parameters called orbital elements or Keplerian elements. There are 6 parameters along with the timestamp, and we're going to talk about all of these. So 2 of them will describe the size and then the shape, whether circular or elliptical, of an orbit. 3 describe the orientation of the orbit in space, different orientations. And 1 will describe the location of the satellite within that orbit. Where is it at? So those are the 6 parameters. First thing that we're going to look at, though, is eccentricity, and that describes the roundness of an orbit. So the describes the shape of an ellipse in terms of how wide it is, and you're going to have an eccentricity between 0 and 1. So you can calculate the eccentricity by taking the square root of 1 minus b squared, or semi-minor axis, divided by semi-major axis squared. Now, if b and a are the same, if it's a circle, so that they're the same value, if you have a number divided by itself, then it just is 1. Well, 1 divided by 1 is 0. So an eccentricity equal to, that's why this says equal to, 0 is just a circle. Otherwise, it's going to be something that is less than 1. If you take the square root of 1 minus something, you're never going to get exactly 1. So what I want you to do is pause this now and calculate the eccentricity of this. Please do that now as a quick check to see if you know how to do it. So you should have come up with a number that is 0.78 for your eccentricity. If you didn't get that, then double check to make sure that your semi-minor axis was b, that's this value on the top, squared divided by 8022 squared, and that should give you a value of 0.39. So we take 1 minus that, and then the square root, we get 0.78. So it is between 0 and 1 for closed orbits. Closed orbits meaning that it's not gaining in altitude. It's not spiraling out or spiraling in. Eccentricity of 0 again means circular, and 1 or greater means the orbit is not closed. So these would be used for interplanetary missions or where it does not come back to the starting point, where it sort of loops around and then it expands and escapes. So note that that's kind of significant. An eccentricity of 1 or greater means that it is not closed, is not going back and continuing forever, but it's kind of looping and escaping. So these are different values of 0 and 1. And this kind of shows you some different orbit types. If you have a 0, it's circular, but also notice what happens to the position with respect to the Earth. As you have an eccentricity of 0.4, then this edge gets quite a bit closer, and we get the far edge gets further out, because the focal point then is going to be in the Earth, the center of the Earth in this case. So that is, especially if you have a satellite, because the satellite is so much less mass than the Earth. So you're going to notice that as the eccentricity value increases, you get much more elliptical, and the Earth gets closer to one edge of this path. And it's possible it could get to the point where the path actually travels through the Earth, in which case that doesn't work anymore because you crash. Beyond eccentricity, orbits may have the same eccentricity but may be different sizes. So here's an example of that. And so that means that there's got to be a Keplerian element that describes the size of an orbit. So these have the same eccentricity, but one is quite a bit larger, and that's how you can compensate for maybe we're getting too close to the Earth, but if the semi-minor axis also increases and the semi-major axis with the same eccentricity, then you're going to get further away from that focal point. and that drag of the Earth's atmosphere as you get close. All right, so semi-major axis. A describes the size of the ellipse. It is half the largest diameter of the major axis of the orbit. The semi-major axis originates from the center of the orbit, right here, but we are located on Earth, so that makes the semi-major axis difficult for us to visualize from our reference point. If we are here and we have a satellite traveling around us, trying to figure out where the center of this ellipse is not just like, you can't just point to it. It's not just like a little red X out in space. So we have to do other calculations to sort of figure that out. But again, the semi-major axis right here describes the size of the ellipse. So here's some other important points on the orbit. So again, pictures to draw out as you write these things down. You have the perigee, which is the point on this semi-major axis that is closest to the Earth, that perigee altitude. And perigee, I'm kind of doing these out of order, but perigee describes the point in an orbit closest to Earth, whereas apogee is farthest from Earth. And those are incredibly important vocab words that you know. And perigee altitude is just this distance. Apogee altitude is this distance, whereas perigee and apogee are points that are on that orbit. For a circular orbit, the apogee altitude equals the perigee altitude. There is not an apogee or perigee because it's really any point along here. Perfectly circular orbits cannot be achieved naturally. Now, artificially with a satellite, you're fighting against atmosphere and you always have to have attitude adjustments. So having something that you consider it's a perfect circle is just a little bit too theoretical in mathematics to get. Now, it's probably conceivably possible, but it's going to take a lot of attitude adjustments to keep it at this exact altitude the entire time. Without corrections, you remember there's going to be orbital decay. So generally circular orbits are described by their altitude, and semi-major axis rarely is used to describe the circular orbits because it's the same all the way around. So if you have a circular orbit, then that's the case. Now again, natural objects never are circular, they're always elliptical, but man-made like satellites and things like that can be very close to circular. All right, now let's take a look at orbital periods. To determine the orbital period, you only need the semi-major axes. And so that's this value here, that's A to the 3/2. You also need the gravitational parameter. You're using the universal gravitational constant, which is always 6.67 times 10 to the -11th. And then in our case, we're taking a look at its period around Earth, so that's your mass of your central body. This is translated as Kepler's third law. The square of the period of a planet is proportional to the cube of its mean distance from the sun. And this square is referring to here, and that's the square of the period of the planet. So that's orbital period. It's proportional to the cube of the mean distance from the sun. So essentially, this orbital period is part of Kepler's third law. So what I would like you to do is see if you can determine the orbital period of this. Now what you're going to notice is that this gravitational parameter u here, or mu, is equivalent to universal gravitational constant times the mass of the central body. So if we have a different central body like the moon or Mars or something like that, then m is going to change. G is always the same. But this is simplified by putting mu in here instead of gm. We could just write it like this. 2 pi times a to the 3/2 divided by the square root of gm, that would be just fine. So if you are actually calculating this out, you need to Google the mass of Earth, and we're doing this in SI units, so it's got to be in kilograms. This is in kilometers, so you're going to have to convert this into meters, because in the previous problem we did for ellipse, they divided out, and you didn't have any units for ellipse. It's just a value. But for this, a period, you are. So SI units for distance are meters. For mass is kilograms. So you're going to have to convert this semi-major axis into meters and put that in here, and then do the calculation to the 3/2. So you're going to need quite a bit of parentheses, or a better way to do it is just to subdivide the numerator and denominator and divide those out and then multiply by 2 pi. So pause this once you're ready and give this a shot, and then I'll fill you in and see how you did. I am hopeful that you got an answer of 7,152, but in SI units, that is just seconds. So that's how many seconds it takes to orbit this. It's 7,152. If we divide by 60, then you're going to get from seconds into minutes divide by 60 again, and you're going to get minutes into hours. So you should come up with something that's very close to 2 hours. I got 1.99 hours as an orbit. Now, one thing to sort of keep in mind that something that's in low Earth orbit is generally only about 300 kilometers versus the Earth, which has a diameter of about 12,500 kilometers. So if your diameter of this is 12,500 and you're only 300 above that, then it really looks like satellites are going pretty much right on the outer edge of this that are in low Earth orbit. So this clearly is not drawn to scale. If the entire diameter of the Earth is 12,000 kilometers, and this is 8,000 right here, the Earth is giant in this. So that's why we really have something that pretty much approximates a low Earth orbit and may not even work because this may end up crashing into the Earth as it's only 5,000 kilometers. On the semi-major axis, and the Earth is too far out. But it's just to mathematically try to calculate that. So what I want you to do next is, if using this, if the period is 1 day, so think about, remember, you have to do period in seconds is what it's calculating. So you need to figure out the number of seconds in a day, and then work backwards and try to calculate if the period is 1 day, what is the semi-major axes. So please pause this, make sure that you are comfortable with this, you know how to do this. If you have questions, call me over because you will have to do this on your quiz. And practicing it now is free. So pause it and give it a shot. This one was definitely tricky. So let's see if we can figure this out. You were trying to solve for it in kilometers if the period is 1 day. So we've kind of shifted this up here. First thing we need to do is convert it to the correct units. So time is always going to be in seconds. So 1 day equals 24 hours over 1 day times 60 minutes in an hour times 60 seconds in a minute, which gives you 86,400 seconds. Really important that you have seconds as your unit. So if you note anything down on this, I guarantee that we're going to have some people get tricked on the quiz and on the final because you're not in the right units. Time has to be in seconds. Distances have to be in meters. So you're going to get an answer here in meters. We have to convert to kilometers. And then mass is always going to be in kilograms. So let's start this out. We have 86,400 seconds. That's our period. Equals 2 pi times a to the 3/2 divided by the square root of g times m. Now I sort of type this out the way that you would see it in your calculator because that is going to cause problems if you don't type things in using the correct amount of parentheses. So the next thing that I would suggest you do is store the square root of gm in your calculator because you're going to have to type this in a lot. And if you remember from the formula here, they place it in mu. So I'm going to store that in u. So if I type in the square root, and I'm going to type these values in, of 6.67, and note that if you use the double E button, that's the same thing as saying times 10 to the power. So I'm going to say 6.67 E negative 11. So you end up with something that looks like this, and then we're going to multiply that by 5.972, or 5.98, E24. And then I hit enter and it gives me this value. Now I want to use this value a lot. So here's how you end up doing that. If we push store down here in the bottom, store, and then I'm going to hit the alpha key and I'm going to store this in the letter U, which is actually the key number 5. So I'm going to hit store alpha 5. And now it says answer is going to be stored in U. And I hit enter. So now anytime I hit type in U or alpha 5, it will come up with that value, the square root of GM. That way I don't have to keep retyping that again and again and again, and then I avoid having that as an error. So my next step is to multiply both sides by the square root of GM or by the value I stored in U. So and this is what I had over here, I'm multiplying the right side, so those cancel out, and then I have to multiply the left side. So when I do that, I get 1.72 E12, which is times 10 to the 12th. And then I have 2 pi times a to the 3/2 on this side. Next, I need to divide by 2 pi. Now, if you do this, if I take that value, 1.72 E12, and I just say divide by 2 pi, it will not work because order of operations says it's dividing it by 2 and then multiplying the answer by pi, not dividing it by the product of 2 pi. So really important, this is a place that I think a lot of people get tripped up, is you need to divide it by parentheses 2 pi. And I'm hoping that this shows up, but you got to make sure 2 pi is in parentheses, otherwise you're not going to get the right value. It's not going to work out. So if you do that correct, you should get 2.74 times 10 to the 11th. And now to get rid of this 3 halves, because I want to know what A is. I want that semi-major axis. Then I take the 3 halves, and I take it to the power of 2/3. So if I take 3 halves to 2/3, they cancel each other out, and I end up with just A. But if I take the right side times 2/3, I have to take the left side times 2/3. So that's how you get rid of this exponent here. You take it to the inverse of that. So if I take 2.74, 10 to the 11th, to the power of 2/3, I end up with this number here, which as it's written doesn't really look like a whole lot. It looks like a bunch of garbage, and that just says meters. I need to divide this by 1,000 to get in kilometers. Now that looks a whole lot better. I'm 42,000 kilometers away. That is my semi-major axis. So that is what you need to do to solve one when you're solving for a semi-major axis. Depending on what you're solving for, the process is going to look a little bit different. But it's possible you may have to solve one for M if it's a different planet, solve one for T, the period, or solve one for A, the semi-major axis. So by showing all your work, and you can see there's a lot of steps in here, it makes it a whole lot easier to see what you're doing. So let's take a look at this little clip, and it shows that different semi-major axes, and these are circular orbits, so semi-major and semi-minor are the same. They're going to have different periods. And that is the end of part 1.